In many situations, we're interested in the relationship between categorical variables and how response categories are distributed across the individuals in a sample. Because these variables are not quantifiable, we cannot use correlation coefficients or any other quantitative analysis. In this presentation, we will learn how to determine whether there is a statistically significant association between two categorical variables. We will do this by conducting a test of significance called the chi-square test. This procedure not only allows us to work with categorical variables, but it also allows us to compare these variables across more than two subgroups. The chi-square test has a test statistic which is called chi-square, so we will also talk about the shape of the chi-square distribution, which has different characteristics from the t and the z distribution. For instance, let's say that a group of researchers would like to determine whether students from a particular university prefer online instruction or traditional face-to-face instruction, and if there is an association between their preference and their educational level, that is, undergraduate or graduate level. To obtain this information, researchers administered a survey and asked students to indicate their educational level and which method of instructional delivery they prefer. The way we organize this information in our data file is to create for each question a categorical or nominal variable to record for each student the educational level and the instructional preference, as shown in the table on the bottom of this page. In this case, we would have two categorical variables, and each variable has two categories. The categories are undergraduate and graduate for the first variable, and online and face-to-face for the second variable. Of course, it is possible to have more than two categories for one variable. For instance, educational level may have three categories, such as undergraduate, master, and doctoral educational level. The instructional preference variable may also include a hybrid category along with online and face-to-face. But for the purpose of this exercise, I decided to just keep things simple so we can focus on the rationale on which this procedure is based. T-tests or Z-tests, depending on certain conditions, could be used to determine whether there are significant differences between two groups, undergraduate and graduate students, between face-to-face and online instruction. However, these procedures would be conducted separately by educational level and then by the type of instruction, and they wouldn't tell us whether there is an association between the two variables. Correlation analysis is typically used to measure the association between variables, but we cannot use a correlation here because the two variables are not quantitative. So what we need to do here is to summarize the data in our file into a table that has the categories of one variable listed in rows and the categories of the other variable listed in columns. This is called a cross-tabulation because we are tabulating two variables at the same time and then count the frequency or the percentage of individuals in each cell of this table or in each subcategory. In this example, we are listing the two types of instructional delivery on two different rows and the two educational levels in two different columns. It doesn't matter here which variable is listed in rows and which one goes into columns. The next step is simply to count how many individuals go into each cell, how many undergraduate students prefer online instruction and how many prefer face-to-face instruction and so on. Of course, we can use statistical software to compute these frequencies for us. We don't actually have to do the counting ourselves, especially when we have a very large sample. But the next question is, how do we know if there is an association between the two variables and whether or not the association is statistically significant? Because we can create crosstabs without conducting any tests, but we would not have sufficient evidence to determine whether the association of the two variables is statistically significant. To determine whether the association between two qualitative variables is statistically significant, we must conduct a test of significance called the chi-square test. The first step is to formulate the null hypothesis for this test. The null hypothesis for the chi-square test is always formulated in words, and it states that there is no association between the two qualitative variables, between educational level and instructional preference in this case. In other words, if there is no association between the two variables, the individuals will be uniformly distributed across the cells of our table. If there are many individuals in one cell and very few individuals in another cell, then it is very likely that there is an interaction between the two variables. The alternative hypothesis for the chi-square test is always two-sided. It is actually multi-sided because the differences may occur in both directions and in each cell of the table. So the alternative hypothesis states that there is a statistically significant association between the two qualitative variables. The second step in conducting the chi-square test is to find the values in each cell of the table when there is no association between the two variables. These values are called the expected values, the values that we expect to see when the null hypothesis is true, when the two variables are not associated. There is a formula for computing the expected values in each cell. We just have to know the sample size, the row totals, and the column totals. In our example, we need to know the total number of students, which is 100, how many graduate and undergraduate students we have. We have 40 graduate students and 60 undergraduate students in our sample. And we also need to know the total number of students who preferred online courses and the total number of students who preferred face-to-face education. And 55 students preferred online courses and 45 of them preferred face-to-face courses. We can then use these numbers to obtain the expected count in each cell using the given formula, which tells us to multiply for each cell the row total by the column total, and then divide this product by the total number of individuals in the sample. The table in the right corner shows us the expected counts for each one of the cells in our table. It is actually very easy to find these numbers even without the formula. For instance, in our example, we have 60 undergraduate students, and we know that 55% of them prefer online instruction. So 55% out of 60 is 33. 45% of the undergrads prefer face-to-face instruction, so 45% out of 60 is 27, or simply the difference between 60 and 33. And the same procedure could be applied for graduate students. Of course, in this example, it is a lot easier to do this by hand because we have exactly 100 students and the percentages are the same as the counts. After computing the expected values, we must see how close these values are to the actual count. The real counts computed from the sample are called observed values. To obtain them, we just have to count how many observations we have in each cell. As indicated in the first table, we have 20 undergraduate students who prefer online instruction and 40 who prefer face-to-face instruction. There are 35 graduate students who prefer online instruction and 5 graduate students who prefer face-to-face instruction. If we use statistical software to conduct the chi-square test, the computer does all the counting for us and computes for each cell both the expected and the observed counts. The table at the bottom of the page shows the table that SPSS creates for our two variables. You can see that in each cell, we have the observed count on top and the expected count right below the observed value. After we know both the expected values and the observed values, we must find out how far are the observed values from the expected ones. Are they different enough to reject the null hypothesis? We need to compute a test statistic that measures the difference between observed and expected values for all the cells of the table at the same time. This test statistic is called chi-square. To obtain the chi-square value, we must compute for each cell the difference between the observed value and the expected counts. Square this difference and then divide it by the expected value. The results obtained from each cell are then added up, and this sum represents the chi-square test statistic. When the observed values are larger than the expected values, the differences are positive, and when the observed values are smaller than the expected values, the differences are negative. However, when these differences are squared, they all become positive regardless of their initial sign. Therefore, the result, the chi-square statistic, will always be positive. It never has values lower than 0. As you can see in this picture, the distribution of the chi-square statistic starts at 0 and can only have positive values. Also, the shape of the distribution looks a little different than what we've seen so far with the t and the z statistics. It starts at 0 and it is skewed to the right. The shape of the distribution changes as the number of degrees of freedom increases. You can see what the curve looks like when we have only 1 degree of freedom and what it looks like when we have 8 degrees of freedom. The number of degrees of freedom for this statistic is not a function of the sample size like we've seen before, but of the number of cells in our table. The DF is computed by subtracting 1 from the number of rows, subtracting 1 from the number of columns, and then multiplying the two differences. Therefore, the more category, or the more cells we have in our table, the larger the number of degrees of freedom. For our example, we only have 2 rows and 2 columns in the table, so if we replace these values in the DF formula, we obtain a result of 1 degree of freedom. The table presented here includes both the observed and the expected values for our example. If we replace these values in the formula for the chi-square test statistic, we obtain the value 28.451. The next question is this value high enough to reject the null hypothesis? The next step in conducting the chi-square test is to determine whether the evidence collected, the chi-square test statistic, is strong enough or large enough to reject the null hypothesis. If we use statistical software, it is very easy to determine this. SPSS, for instance, computes chi-square for us, along with a series of other coefficients. For the purpose of this analysis, all we need is the Pearson chi-square statistic. We can see that the degrees of freedom is equal to 1, and the p-value for the chi-square statistic is almost equal to 0. Because this value is lower than alpha of 0.05, we should reject the null hypothesis and accept the alternative hypothesis that there is a significant association between students' educational level and their preference for online or face-to-face education. If we go back to our crosstab, we can see that the majority of graduate students preferred online instruction, whereas the majority of undergraduate students preferred face-to-face instruction. If we conduct the chi-square test by hand, after we compute the test statistic, we can compare it to the critical value that corresponds to our degrees of freedom and significance level. This critical value can be obtained from Table D in your textbook at page 680. For that, we need to know alpha, which in our example is the typical value of 0.05, and the degrees of freedom, which in our case is equal to 1. The rows of the table show the degrees of freedom and the columns show the significance level. For alpha equal to 0.05 and 1 degree of freedom, the chi-square critical value is 3.84. This value is much smaller than the test statistic, which was 28.4. Therefore, we should reject the null hypothesis. The chi-square curve looks a little different than in this figure when the df is equal to 1, but this was the only image I could find. I used it anyway though because it is helpful to see as a general principle that chi-square test statistic must be further to the right than the chi-square critical value to reject the null hypothesis. When chi-square is statistically significant, the next step is to decide where the significant differences occur. There are coefficients that we could compute for this purpose, but for now we could just visually inspect the distribution of the values across the cells of the table and identify the cells with the largest discrepancies between observed and expected values, and whether the observed values are smaller or larger than the expected values. In our example, large discrepancies between expected and observed values were recorded for both graduate and undergraduate students. For instance, only 5 graduate students preferred face-to-face instruction compared to the expected value of 18. Similarly, only 20 undergraduate students preferred online instruction, and the expected value was 33. Therefore, we can conclude not only that there is an association between the two variables, but we can describe this association by saying that graduate students preferred online instruction, whereas undergraduate students preferred face-to-face instruction. One important assumption that we have to meet when using the chi-square test is to have expected counts that are equal or greater than 5, and to have observed counts that are at least 1 in each cell. Fortunately, we don't have to have large sample sizes, but we must have an expected count of at least 5 and an observed count of at least 1 in each cell of the table to be able to test the p-value for our chi-square test statistic. Chi-square test can be used both with independent samples, like we did in our example when we collected 2 random samples from 2 different populations. In our case, the 2 populations were the population of undergraduate students and the population of graduate students. In other research scenarios, we may have a single random sample and each individual is classified on 2 different categorical variables. Therefore, we have 2 classifications for each individual and the 2 classifications are compared.